Welcome to The Explainer. Today we're going to do something pretty incredible. We're going to take the sometimes, intimidating world of statistics and transform it into a thrilling detective investigation. Because, let's be honest, if you've ever stared at a spreadsheet full of raw numbers or some complex software output and just felt totally overwhelmed, you are definitely in the right place. Today, we're putting on our detective hats, we're using SPSS as our magnifying glass to unlock the hidden secrets buried deep inside your data.
To kick off our investigation, I want you to think about a mystery we can all relate to. How exactly do insurance companies predict your exact car premium? I mean, is it just a wild guess? Are they shaking a magic 8-ball in the back room? No, absolutely not. The answer lies in becoming a data detective and utilizing the incredible power of statistical prediction. Today, we're actually going to crack this exact case using real data. And by the end of this explainer, you're going to know exactly how the math behind the curtain really works.
Okay, so let's dive right in by establishing a fundamental rule for our investigation early on. In the data detective world, we basically have two main tools: correlation and regression. Now, correlation, that's simply about spotting a connection between suspects. It's kind of like noticing that people who buy umbrellas also tend to buy raincoats, right? It tells us they move together, but honestly, not much else. Regression, on the other hand, well, that's the heavy machinery. It's the tool that proves the cause and literally predicts the future. It doesn't just say, hey, these two are connected. It tells us exactly how much one thing changes when another thing happens. It's a real game changer.
All right, let's move into phase one, profiling the suspects using descriptive statistics.
Before we start predicting the future, we just need to describe the basic clues we already have on hand. Now, when you look at this standard SPSS output, don't let it intimidate you. It's simply a basic profile of 50 students' statistics grades. If we just scan down the column, our mean, or the average grade, is 11.06. And right below that, the standard deviation is 4.76, which just shows us how much those scores are scattered around the average. See? Not so bad. We're just building a basic profile of our classroom suspect.
But let's look a little deeper at a very specific, absolutely vital clue extracted right from that same table. I'm talking about the skewness. We've got a negative skewness number of negative 0.371. In our detective work, this tells us the data tail stretches out to the left. Statistically speaking, this means the bulk of the scores were actually on the higher end, but a few really low scores pulled that tail down. So what's the real-world verdict here? Well, it tells us the exam was actually quite difficult, but most students still managed to push through into the higher ranges.
Now, before we move on, remember, a good detective always verifies their evidence. We need to know if our data actually behaves normally. And in SPSS, it's just a few simple clicks. We go to Analyze, down to Non-Parametric Tests, over to Legacy Dialogues, and finally, we hit the one-sample KS test. When you run this, you're really just looking for one magic number, and that is the sig value. If your resulting sig value is over 0.05, congratulations, your data clears the normal distribution test, which means we can safely break out all our advanced statistical tools.
Moving right along to phase two, discovering hidden connections.
Now it's time to look for the actual relationships between our pieces of evidence. When we're hunting for these connections, we basically have two different magnifying glasses to choose from. And the rule of thumb here is super simple. You use the Pearson coefficient for exact, measured quantities. Think things like money or weight. But you're going to want to call in Spearman when you're dealing with ranked categories, like student grades ranging from poor to excellent. Make sense?
Okay, this is where it gets really fun. Phase 3. The future prediction machine. To build this prediction machine, we use a formula that, kind of looks like alphabet soup, but I promise you it's just a simple recipe. Y equals A plus BX. Let me translate that for you. Y is the ultimate outcome we want to predict, which, in our insurance case, is the car premium. A is our starting baseline, basically the fixed cost if absolutely everything else was zero. And B? Well, B is the secret sauce. It tells us exactly how much that premium changes with every single year of driving experience, which is represented by our X.
Now, I know what you're thinking. Looking at this complex ANOVA and coefficients table, it just looks like a whole lot of noise. But don't worry, ignore the noise. We just need to focus on how we solve the mystery using a few specific rows. This right here is the actual output calculating the relationship between a driver's years of experience and their insurance premium. All we have to do is pluck our recipe ingredients straight out of this table.
So the most crucial clue is nestled right at the bottom in that coefficients table. We pull out the B coefficient, and look at that. It's negative 0.298.
Guys, this is our golden ticket. That negative sign proves an inverse relationship. It mathematically proves that for every single year of driving experience a person gains, their insurance premium magically drops by 0.298 units, which in this specific case means thousands in whatever currency we're using. Experience goes up, the premium goes down. We have literally quantified the exact value of driving experience.
And this perfectly illustrates just how strong our case really is. If we look at the R-squared value from our model, which sits at 0.8642, we can visualize the whole truth. Over 86% of the entire insurance premium's cost is explained entirely by the driver's experience alone. That leaves only about 13.5% to other unknown variables. Think about that. We didn't just guess, we have successfully cracked the case with overwhelming, undeniable evidence.
And that brings us to our final step, Phase 4, decoding the verdict.
So, our prediction machine looks great, right? But how do we actually prove to a jury that this isn't just some random fluke? Well, here's the golden rule you absolutely must commit to memory. If the SIG value is less than 0.05, we have a statistical smoking gun. Let me repeat that. Less than 0.05 is the smoking gun. It means we have less than a 5% probability that these results just happen by mere chance.
And when we look back at our insurance model's ANOVA table, the SIG value given by SPSS is 0.000. Now, don't be fooled here. In SPSS, this doesn't actually mean absolute zero. It actually means the value is so tiny, it's less than 0.001. So what's the verdict? It is highly significant and definitively not due to chance. Our regression model is rock solid, case closed with absolute certainty.
We've gone from asking a simple question to building a mathematical machine that proves exactly how experience lowers insurance costs. So, I want to leave you with this thought. If raw data can be decoded to predict an insurance premium this accurately, what hidden secrets, what powerful future predictions are just waiting to be uncovered in your own business or academic numbers? Really think about it. Your data is just an unsolved mystery, waiting for you to investigate. Thank you so much for joining me on this explainer, and hey, happy sleuthin'!